Glycation is tightly tied with aging and chronic disease, but a low-carb diet is not the answer. I'll tell you what the best diet is for glycation in today's episode of the Energy Balance Podcast, a podcast where we explore health and nutrition from the bioenergetic view and teach you how to maximize your cellular energy to maximize your health. In today's episode, I'll be going over how glucose and insulin can actually decrease glycation. I'll also discuss why ketogenic diets can be worse than high-carb diets when it comes to age formation. I'll go over how autophagy helps to clear ages, but why increasing autophagy is not the answer. I'll also discuss the true primary drivers of age accumulation and the best diet and supplements for minimizing glycation. As always, to take a look at the show notes where I'll link to the articles, studies, and anything else that I reference throughout today's episode, you can head over to jfeldmanwellness.com/podcast. And with that, let's get started. All right. So in the last episode, we dug into some mechanisms, some physiology about the formation of ages and glycation from different substrates, sugars like glucose and fructose, but also fatty acids, amino acids, ketones. And we talked a bit about the context of what drives glycation and what drives the formation of advanced glycation end products. And we'll start off today by going into a bit of the physiology about the detoxification of these different glycation products and also the clearance of the advanced glycation end products. And then we'll talk about more of the application, how this applies to different diets and supplements and things like that. But this is important. This other side of the equation is very rarely given any lip service. Normally, it's all about what causes glycation, what forms these advanced glycation end products, but not about the other side, about what clears them out and protects us from them, which is really important because, as we'll talk about, in the states with increased glycation, in the states with increased or accumulated advanced glycation end products, part of the issue is the formation, but part of the issue is a lack of clearance and a lack of detoxification. So we'll start here by talking about that side of the equation. The first being the detoxification of some of the earlier glycation products and the intermediate glycation products, which can actually be detoxified, meaning that they're converted into other metabolites, other things that aren't so concerning. And then we'll talk a bit about the clearance of the advanced glycation end products. And those are relatively permanent so that we can actually convert them back into other less harmful things. We just have to clear them out of the system. And so we have this graphic here showing both sides of the kind of clearance and detoxification along with the formation. So we can see here in this graphic at the top, we have the dicarbonyls. As we talked about, these are the glycating agents that we want to be most concerned about. And they mentioned some other sources here. And we can see methylglyoxal in particular. And we can see that it can go over to the left through the primary detoxification pathway, which is the glyoxalase system. So we'll be talking a bit about this. This is a system that requires glutathione. And in the case of methylglyoxal, it converts it into D-lactate. So that's one way that it can be cleared. And as you can see, there are some alternative pathways as well, which we won't touch on too much, but there's a handful of different ways that these dicarbonyls, which are intermediate glycation products, can be cleared or detoxified in this case. And then if they do continue on to actually form those advanced glycation end products, at that point, they can't be detoxified. They can't be converted to something less harmful. So we have a couple of different ways that we can clear them. And we can see this on the right of the diagram, that there's clearance through these proteolytic pathways. We have the ubiquitin proteasome system, which is abbreviated UPS. And then we have autophagy. So we'll be talking about those two different forms of clearing ages. And then you can also see at the very bottom here, if we don't have enough clearance or detoxification, then we can end up with the accumulation of ages and some of those negative effects there. So that's our broad overview. And we'll start by talking about the detoxification specifically of the dicarbonyls like methylglyoxal via the glyoxalase system. And so there are a couple of important things to note here, which is that the glyoxalase enzymes require glutathione. This pathway requires glutathione. Glutathione is known as our master antioxidant. And so this is part of why glutathione is very important. And along with this pathway, this glyoxalase pathway, is going to be inhibited under states of increased oxidative stress due to the glutathione depletion that occurs in that state. Basically, if there's a lot of oxidative stress and damage going on elsewhere, it depletes glutathione, which leaves less glutathione available for this glyoxalase system. And so we see a bit of a discussion of this, the regulation here of glutathione and how it is able to detoxify methylglyoxal in this study. And we're going to take a look at this study titled Methylglyoxal Glyoxalase 1 Balance, the Root of Vascular Damage. And they state under physiological conditions, greater than 99% of methylglyoxal is detoxified by the glyoxalase system. So we had seen earlier in that diagram, there are some other more minor pathways, but the vast majority is going through the glyoxalase pathway. They go on to state the glyoxalase system consists of glyoxalase 1, glyoxalase 2, and a catalytic amount of glutathione. Acting as the rate-limiting step, glyoxalase 1 catalyzes the primary detoxification step. Its activity is directly proportional to glutathione concentration. Thus, when cellular glutathione concentration declines as an oxidative stress, glyoxalase 1 activity is impaired. So this is something we were just touching on, which is basically that this glyoxalase pathway is, of course, primarily responsible for the detoxification of methylglyoxal. Its activity is directly proportional to the glutathione available. And so if we have a state of oxidative stress, which we see in different metabolic conditions, and we'll get into in a moment, then we're going to see impairment in this pathway. And so one of the conditions where we see this is insulin resistance. And we talked about this in the last episode, where in insulin resistance and diabetes, you see an accumulation of different glycation products. And part of the reason for this is due to not just the increased production, but also the impaired clearance and detoxification through, in this case, the glyoxalase pathway. And they touch on that here in this study titled The Critical Role of Methylglyoxal and Glyoxalase 1 in Diabetic Nephropathy. And they state methylglyoxal is a highly potent glycating agent with specific reactivity of around 20,000-fold higher than that of glucose. This is tolerable in vivo because efficient detoxification of methylglyoxal by glyoxalase 1 maintains the concentration of methylglyoxal in plasma approximately 50,000-fold lower than that of glucose. So we talked about this in the last episode, methylglyoxal being 20,000 times more reactive than glucose, but luckily we have this glyoxalase pathway to help keep it in check. They go on to state in diabetes, however, methylglyoxal concentrations and methylglyoxal-derived ages increase in plasma and at sites of complications development. They go on to state methylglyoxal is formed mainly inside cells, but a minor fraction leaks out, and so glycation of both cellular and extracellular proteins by methylglyoxal increases. So the important point here being, well, there's a couple. One that we talked about in the last episode is that most glycation is occurring in the tissues, not in the plasma. And they do touch on that here. And they also touch on the fact that we see an increasing concentration of methylglyoxal in this state of diabetes and insulin resistance. And they also show in this diagram here that what's actually going on in this state is decreased glyoxalase. You see that arrow at the bottom, that there's a decreased activity of glyoxalase to help clear out that methylglyoxal, and that being one of the main things responsible for the accumulation of methylglyoxal and then also advanced glycation end products in the case of diabetes. So with that in mind, when it comes to this detoxification system, which is essential for keeping glycation in check, for clearing out these glycating agents that are really highly reactive that we want to, be careful about, there are some things to consider that will help support this pathway and help support glutathione. And the first to touch on, and this might be surprising, is actually carbohydrates and insulin. Both of these are very much supportive of this glyoxalase pathway. And so, we talked in the last episode about this misconception that's spread quite a bit, that glycation is just driven by carbohydrates. And if you eat more carbohydrates, you're just going to have more glycation. The reality is very far from that. There's a lot of other substrates that cause glycation, and the real driver of glycation goes a bit deeper and has to do with some metabolic issues. On top of that, when we look at the other side here, the clearance of these glycating agents and these intermediate glycation products, having carbohydrates is actually really, really important and protective. It actually helps to support this pathway. This is also the case with insulin, which of course is largely demonized, but insulin supports the detoxification of the dicarbonyls like methylglyoxal by increasing glutathione synthesis. So we have more glutathione available, and it actually increases glyoxalase expression. So you have more of these enzymes in the glyoxalase pathway to actually clear out these dicarbonyls. And I'd referenced one of Chris Masterjohn's articles in the last episode talking about the dicarbonyls, and he has another one titled Sugar is the Ultimate Antioxidant and Insulin Will Make You Younger, talking a bit in more detail about the benefits of insulin and carbohydrates for detoxifying these glycating agents. So I would highly recommend checking out that article. So that's the first piece as far as insulin goes, but then we also have glucose itself being beneficial here. And one of the mechanisms for that is that glucose encourages the regeneration, or it supports the regeneration of glutathione via what's called the pentose phosphate pathway. And so you can see that here, this is one of the pathways that glucose can undergo, and it regenerates what's called NADPH, which we need to regenerate the reduced form of glutathione. This is the glutathione that's active, that's able to help in the glyoxalase pathway and work as an antioxidant elsewhere. And so glucose is actually, extremely important for making sure that we have enough glutathione available and in the form that actually allows it to function as an antioxidant. In this metabolic state that we were talking about, insulin resistance, and we've done a handful of episodes before talking about why insulin resistance is not actually caused by carbohydrates. It's not caused by glucose or fructose. And I would highly recommend checking those out. But interestingly, in these states of increased oxidative stress and inflammation, what we find is that insulin itself is actually still supportive. So even if you have this state of insulin resistance, having more insulin is actually helpful for increasing glutathione synthesis and increasing glyoxalase expression. And they describe this here in a study titled "Insulin Decreases Intracellular Oxidative Stress in Patients with Type 2 Diabetes Mellitus." And this is a study where they did what's called a hyperinsulinemic clamp in patients with type 2 diabetes, where they basically kept insulin levels artificially high. And what they found was that it actually restored glutathione and lowered oxidative stress. And they state that here, where they state patients affected by diabetes mellitus have oxidative stress with an impaired glutathione redox state. We found a significant elevation in the GSH to GSSG ratio. So this is the reduced to oxidized glutathione ratio after 2 hours of incubation with insulin in erythrocytes from diabetic patients. So, we were seeing earlier the regeneration of the reduced form of glutathione that works as an antioxidant. And that's what we're seeing here, basically, that insulin increased the functional form of glutathione that's effective, that we want. And that's what they saw in this case. They went on to state that during the clamp studies, the reduced oxidized glutathione ratio had already increased after 60 minutes and even more after 120 minutes. We conclude that insulin in patients with type 2 diabetes mellitus can reduce intracellular oxidative stress through increased reduced to oxidized glutathione ratio. So pretty remarkable here. Again, this is in a case of type 2 diabetes in a situation where there's a lot of metabolic stress, obviously not an ideal health state, and yet providing more insulin was actually helpful. Obviously, I would say that dumping insulin on the state is not the way to fix it, but definitely points to the fact that not only is insulin not the culprit here, not only is it not actually causing this issue, but is actually very supportive and helps with the opposite side of glycation and clearing these glycation products. Now, moving on to that next step, which is the clearing the advanced glycation end products through those two different pathways we talked about, one being autophagy and one being the ubiquitin proteasome system, the UPS. We're going to dig into each of these pathways in a little bit more detail, just because there's a number of ways that they translate to other things that we talk about a lot, like hormesis being one of them, as one of these kind of primary perspectives in the alternative health space as, a way toward improved health through increased stress. And autophagy is kind of a mediator there, where autophagy is looked at as a good thing, where we want to do anything we can to increase autophagy, and with the idea that it's going to clear out damaged proteins and various other harmful, compounds, with the ages being one of them. But as we'll get to, it's not quite that simple. But let's just start by looking at this study, which is titled "Glyoxalase System as a Therapeutic Target Against Diabetic Retinopathy," and just kind of describing the general process of clearing these advanced glycation end products. And we'll also look at a diagram here. In the quote, they state, "Although ages are irreversible adducts and cross-links in our tissues, these can be removed through different proteolytic capacities. Ages are substrates of intracellular protein degradation pathways, and two major proteolytic capacities are suggested to contribute to the clearance of ages: the ubiquitin proteasome system, UPS, and autophagy." And then we have this figure here where we can see these two different processes at play. So, we see the increased methylglyoxal in the center there that they're saying, is occurring as a result of diabetes. And we also see the glyoxalase system that we already discussed over on the top right. But then as the methylglyoxal becomes ages, there are two different pathways that it can be cleared through the left. One is that UPS pathway, and then autophagy. So let's talk about those pathways in a little bit more detail and what regulates them. Now, as we'll get to in a moment, when we get into these pathways, simply increasing autophagy with hormetic interventions, things like cold plunges, fasting, various supplements, is not actually the answer for clearing advanced glycation end products or for improving our metabolic health. But if you are looking to improve your metabolic health, maybe you're dealing with low energy symptoms like chronic cravings and hunger, low energy or fatigue, chronic pain or joint pain, weight gain, digestive symptoms, brain fog, poor sleep, hormonal imbalances, or various low energy chronic health conditions like autoimmune conditions, high blood pressure, insulin resistance, or various other chronic health issues you might be dealing with, then head over to jfeldmanwellness.com/energy, where you can sign up for the free Energy Balance mini course, where I'll walk you through the best diet, exercise, and lifestyle strategies so that you can resolve these low energy symptoms and chronic health conditions by maximizing your cellular energy. So again, head over to jfeldmanwellness.com/energy to sign up for the free Energy Balance mini course. And with that, let's talk a little bit more about autophagy and why simply increasing autophagy is not actually the answer here, even though it seems like it might be, right? Because if autophagy is one of the things that helps to clear these advanced glycation end products, wouldn't we just want to do anything that we can to increase autophagy? Well, the first thing to note here, and we talked about this a lot, we did a whole hormesis series. I wrote a couple of really lengthy articles discussing this. But when there's oxidative stress and damage, when there are, harmful, cross-linked proteins, when we have these advanced glycation end products, when there are things that we want to clear, the detoxification systems, the clearance systems are already activated. These things act as the signals for the antioxidant pathways and for things like autophagy. So if there's oxidative stress, and we're talking about some chronic health issue or even a short-term oxidative stress, whether it's from fasting or something else, all of those activate the defense systems. And so this idea that the problem, if somebody has accumulated ages, is that they haven't activated the autophagy pathway enough is completely backward, because this is a state where the body has already been trying to activate that pathway. All of the signals for that pathway have already been activated, and yet they're still not actually functioning properly. And, a kind of crude analogy I often will mention is, it's like we have a really messy room, and normally that would tell us like, hey, we need to clean it. And maybe a parent comes into the room and, sees that it's really messy. And so instead of, doing something to help us clean it or something like that, they make the room messier to try to make it more clear that we should be cleaning the room. But that wasn't actually the problem in the first place. It was already obviously messy. And so it's kind of a similar scenario here. And one of the reasons for that is because the advanced glycation end products themselves are actually part of the mess, and they already stimulate the activity of autophagy and the UPS, the ubiquitin proteasome system, on their own. You don't need to add stress from cold plunging or fasting to activate the systems. If you're worried about accumulated ages, they're already activating these pathways. And they discuss that here in this study titled Protective Role of Autophagy in Age-Induced Early Injury of Human Vascular Endothelial Cells, where they state, advanced glycation end products contribute to the pathogenesis of diabetes mellitus and atherosclerosis by promoting vascular endothelial cell proliferation, migration, damage, and death. These results suggest that the age BSA increases the level of autophagy, which is protective against injury, and that ROS play a role in this activation of autophagy. So this was, I cut a section of the quote so that it was a little bit more succinct, but in this study here that they were looking at, what they found was that the advanced glycation end products were triggering autophagy through reactive oxygen species, and that, the autophagy is protective against the damage. Obviously, what we get to in chronic disease states is basically overwhelming this detoxification system, and other things actually go on that impair the detoxification system, much like what we saw in the glyoxalase pathway with glutathione. There are some parallel things that happen here. We'll get to those in a second. But before we get to that, it's worth going through a couple of examples here. And we'll go through just a couple of short quotes from two other studies describing how the basically issues with autophagy, both too little and too much, play a role in chronic health conditions. And so this first study here is titled Autophagy and Neuronal Cell Death in Neurological Disorders. And they state, inhibiting autophagy has been reported to be beneficial in several neurodegenerative states, the clearest example being hypoxic ischemic brain injury. Beneficial effects of autophagic inhibition have also been seen in several models of chronic neurodegenerative diseases. So what they're talking about here is actually that in many situations, autophagy is actually a part of the issue and actually causes some negative effects, which just once, is important to recognize, important to note that we don't just universally want to be activating these detoxification pathways, these clearance pathways, if there's not a reason to. It's not inherently good to be activating them, and they're actually implicated in some negative conditions. And this is touched on in the next study as well, which is titled, Autophagy Plays a Double-Edged Sword Role in Liver Diseases. And they state, in hepatocytes, autophagy is not only essential for homeostatic functions, but also implicated in some diseases such as viral hepatitis, alcoholic hepatitis, and hepatic failure. Taken together, further exploration is necessary, and downregulating the level of autophagy may become a new strategy for the treatment of liver fibrosis. So again, talking about in these different liver diseases, that excess autophagy is actually a part of the pathology, is actually a negative thing. So again, further reason to be careful when it comes to just kind of universally wanting to increase autophagy. But as we'll get to the other detail here, which is that in these states, the signals for autophagy are already there, right? The cell's already asking for autophagy. The signs of damage are already there that are saying, hey, we need, some cleanup. And yet it's not able to actually properly be carried out. And so one of the main reasons for that actually comes down to energy, and specifically ATP, right? The cellular currency of energy, which is necessary for proper autophagy. It's also necessary for minimizing oxidative stress. And what we see in some disease states, and a few different examples that we'll go through here, is that a lack of ATP is actually part of the problem that's preventing autophagy from happening in situations when it's supposed to happen. And that could lead to, an accumulation of, in this case, advanced glycation end products. The problem is not that we haven't stimulated autophagy enough. It's that we can't properly undergo autophagy because of a lack of ATP, a lack of energy. And we'll start with this study discussing this. This is a study titled, Moderately Reduced ATP Levels Promote Oxidative Stress and Debilitate Autophagic and Phagocytic Capacities in Human RPE Cells. These are retinal pigment epithelium cells looking in the eye. They state, a tractyloside treatment reduced cellular ATP levels by 30%, mimicking the energy status of aged RPE. So what they were basically looking at was cells from aged to old, I believe humans, that had 30% lower levels of ATP. And so they were trying to mimic that using something that blocks ATP production. They're using a tractyloside in this case. But so basically they decreased those ATP levels by 30%. And what they found was that TBH decreased reduced glutathione in RPE cells with lowered ATP levels, whereas cells with normal ATP content were not effective. So TBH induces oxidative stress. It's basically a harmful compound. And what they found was that it was depleting glutathione in the cells that already had lowered ATP, but when there was normal ATP, it wasn't an issue. They go on to state that TBH-induced oxidative stress resulted in substantial accumulation of MDA malondialdehyde protein adducts in cells with lowered ATP, while cells with regular ATP levels were only modestly affected. TBH induced more oxidative DNA damage in cells with lowered ATP levels than in cells with regular ATP. In the tractyloside-treated cells, autophagy rates decreased threefold as compared with controls. Phagocytic capacity for uptake and degradation of photoreceptor segments was reduced in RPE with low ATP. So to go back through this a little bit, because there's some really important points here. One is the accumulation of malondialdehyde. This is an aldehyde that's produced from lipid peroxidation, which we talked about in the last episode is actually a major driver of glycation and can form advanced glycation end products. So that aldehyde accumulated in the cells with lower ATP. Also, we saw oxidative DNA damage in the cells with lower ATP. We also saw autophagy decrease by threefold in these cells with lower ATP. Again, all of the other conditions the same. And that phagocytic capacity, which goes hand in hand here, we're talking about the clearance of damaged proteins and other damaged components of the cell, that was also reduced in the cells with low ATP. And they conclude by saying moderately decreased ATP levels, such as seen in aged individuals, might contribute to the vulnerability of RPE to oxidative stress damage and to dysfunction. So, a pretty good overview here demonstrating how much of an impact decreased ATP levels can have when it comes to not only autophagy, but just this general state of damage and impaired clearance. We'll go through a couple of other examples here that, again, are pretty telling. And so this next study is titled Autophagy is Impaired in Neutrophils from Streptozotocin-Induced Diabetic Rats. They state, evidence is presented herein that autophagy is impaired in neutrophils from diabetic rats. Malfunctioning mitochondria and decreased ATP content have been associated with impairment in autophagy and shortened neutrophil lifespans as indicated by the increased content of cleaved caspase. The increase of free fatty acid oxidation in neutrophils from diabetic rats might then be associated with mitochondrial dysfunction or depolarization, and so decreased intracellular ATP content. Low levels of ATP increase the DNA fragmentation susceptibility, and so cell death through increased oxidative stress. So a couple of important points here. And again, this has obviously been a theme between last episode and this one, which is impairments in mitochondrial function, decreased ATP production, impaired energy production is a major driver here. And in this case, we're seeing, again, reduced autophagy, increased oxidative stress, and they're actually pointing to increased fat metabolism, increased fatty acid oxidation in these cells and diabetes, which is something that we see being one of the drivers of mitochondrial dysfunction and decreased ATP content, which is, again, something that we see. And again, another reason why we don't want to be driving up fat metabolism by cutting carbs or by fasting or by inducing other forms of stress, like, cold plunges and things like that. It's actually, again, in the long term, this sort of stress makes something that interferes with mitochondrial function, decreases ATP availability, and is going to, in this case, actually impair autophagy. Again, in the long term, even though in the short term, you're creating a lot of damage and, yes, increasing or upregulating that process. Again, just to be clear, when we're talking about these disease states, like diabetes, this is not a state where there's not enough signals for autophagy. There's already tons of signals asking for more autophagy. The problem is impaired mitochondrial function and increased oxidative stress, preventing that from occurring, and adding more oxidative stress and damage through the cold plunge or through fasting or through a low-carb diet or through a supplement like resveratrol is not going to fix that issue. And you're not actually going to be able to increase the autophagy, even if you wanted to in that state, because of the metabolic issues, which you're actually just making worse. All right, continuing on here, just a couple other studies that are, again, pretty telling here. The next one titled, Glucose Induces Autophagy Under Starvation Conditions by a P38 MAPK Dependent Pathway. They state, it's commonly accepted that glucose inhibits autophagy since its deprivation from cells cultured in full medium induces autophagy by a mechanism involving AMP kinase, mTOR, and ULK1. So what they're talking about here, and this is something that you really commonly hear, is that carbohydrates inhibit autophagy. And so a low-carb diet is what you want to increase autophagy. And it's coming from this sort of scenario where, again, the deprivation of glucose, taking away the fuel, depletes energy, depletes ATP, which increases AMP kinase, and that's one of the signals for increased autophagy. Again, we don't need that signal. That's not the problem in any disease state. We already have that signal there because of oxidative stress and low ATP as it is. But we know that, lack of glucose will definitely cause that. But they go on to state, however, we've shown in the present study that under starvation conditions, addition of glucose produces the opposite effect. Specifically, the results of the present study demonstrate that the presence of glucose induces an increase in the levels of LC3-2 and the number and volume density of autophagic vacuoles and in protein degradation by autophagy. I know that was a mouthful, but basically what they're finding is that in the state of stress where, we need to actually be able to properly respond to it, autophagy being one of those things, we need ATP, and glucose is a great source of it. They go on to say addition of glucose also increases intracellular ATP, which is in turn necessary for the induction of autophagy. Because the glycolysis inhibitor oximate inhibits it, there's also a good correlation between LC3-2 and ATP levels. So basically what they found was that glucose was able to restore autophagy, and it did so by increasing ATP. When they blocked the ability to metabolize the glucose, you lost the ATP and you lost the autophagy. So this idea that carbohydrates, glucose, sugars in general interfere with the antioxidant pathways or interfere with autophagy is not at all the case. Basically, it's just built on this faulty idea that because when you deplete glucose, you induce stress and that causes autophagy. That doesn't mean that glucose impairs autophagy. And again, this is the type of evidence that is normally used in support of hormesis. And this is one of the many examples of the problems with that thought process. And again, talked about that extensively. And that brings us to one other factor that's important when it comes to consuming carbohydrates and not inducing too much stress on your body, which is the state of the thyroid. And having adequate thyroid hormone is also necessary and supportive of autophagy. We can look at that in a short quote from this study titled Thyroid Hormone Mediated Autophagy and Mitochondrial Turnover in Non-Alcoholic Fatty Liver Disease, where they state recent findings suggest that dysregulation of mitochondrial homeostasis and autophagy play critical roles in the hepatocyte injury and insulin resistance of non-alcoholic fatty liver disease. Thyroid hormone is a major stimulator of hepatic autophagy and mitochondrial function. And in our thyroid series, we talked extensively about why carbohydrates are so important for thyroid hormone production and conversion. And, we see here that, again, this is another one of those mechanisms through which having adequate carbohydrates is actually supportive of our detoxification pathways, supportive of pathways like autophagy. And this is also the case with the other system that's used for advanced glycation end product clearance, the UPS system. And we'll just look at one study here showing that ATP availability and mitochondrial function is also needed. And so this is a study titled Mitochondrial and Ubiquitin Proteasome System Dysfunction in Aging and Disease, Two Sides of the Same Coin. And they state a decrease in cellular ATP levels and an increase in reactive oxygen species production can impair proteasomal function by affecting protein ubiquitination and proteasome assembly and stability. So this is basically saying that a decrease in energy, decrease in ATP, and an increase in ROS or oxidative stress impairs this UPS function. They go on to state evidence that mitochondrial dysfunction might affect proteasomal activity has been reported in different systems, including yeast, C. elegans, and mammalian cells. It's been shown that inhibition of oxidative phosphorylation, this is energy production, in rat-derived cortical neurons also affects proteasomal activity and protein ubiquitination. Again, this is that UPS system that we need for clearance of the ages. And in this last quote, they state ATP is required for both protein ubiquitination and proteasome assembly and stability. Intracellular ATP levels have been shown to regulate proteasomal activity both in vitro and in cultured cells, and manipulation of intracellular ATP levels by inhibition of complex 1 has been shown to decrease proteasomal activity in primary mesencephalic cell cultures, an effect which was counteracted by increasing the glucose concentrations in the cellular medium. So we see it again here with this UPS system, this other system that's needed not just for clearing advanced glycation end products, but for other damaged proteins as well, where not only are ATP levels directly implicated and mitochondrial function also is directly implicated, but also providing enough glucose is very supportive of this process as well. So to kind of conclude this whole other side of the glycation section, what we basically have is a scenario that's very similar to the first one, which is that metabolic dysfunction, like a lack of ATP, interfered with mitochondria, which is caused by all sorts of factors, and we'll talk about some of those today, is the primary driver of the other side of the advanced glycation product accumulation, which is a reduced clearance of the ages and reduced detoxification of these glycation products. And again, this is another scenario. Carbohydrates and insulin are actually very supportive of this clearance and this detoxification, as opposed to being drivers of it. Again, very much the opposite of what we're often told. So with that, let's move on and talk a little bit about some different diets, high-carb diets versus low-carb diets when it comes to advanced glycation end products. And so we'll start here talking about the high-carb diets. And again, we're generally told that high-carb diets are the issue. Don't want to be eating a lot of glucose, don't want to be eating a lot of fructose. And the main reason being that these diets cause spikes in blood sugar. They cause your blood sugar to be elevated on a more chronic basis. They cause insulin to be elevated on a more chronic basis. These two things together cause insulin resistance. They cause impaired mitochondrial respiration. This is actually going to be the thing that causes metabolic issues. So you want to avoid carbohydrates for this reason. This is that kind of general narrative that we're told. And then along with that, as a result of chronically elevated blood sugar and this impaired metabolic function, that's where you see increased glycation. That's generally the mechanism that we're told. But the reality, and again, we've talked about this in these previous episodes on insulin resistance, is that the underlying factor in this state of insulin resistance is impaired metabolic function to begin with and impaired glucose utilization. And that's why we see this buildup of glucose, the buildup of intermediates, elevated blood sugar. It's not actually caused by the carbohydrates themselves. They're just kind of the byproduct here. And along with this, we know that there are tons of examples. I'm not going to go through these in detail because we've talked about these extensively, many, many times. But there are tons of examples, tons of studies showing that high carbohydrate diets improve insulin sensitivity and improve blood sugar regulation. They improve the metabolic state when glucose is provided as a fuel and basically allow us to utilize that sugar better so that there's less available for glycation, as we talked about in the last episode. And then we also see this in native cultures that have consumed high-carb diets for their entire lives, and they have incredible insulin sensitivity. They have really good blood sugar regulation. Their glucose tolerance test values are remarkable, where they use glucose incredibly well, quote unquote, despite consuming high-carb diets for their entire lives. So there's, again, a ton of literature on this. I'll link back to episodes where we've talked about it before, but there's general narrative that, the high-carb diets are going to cause glycation, insulin resistance, elevated blood sugar, and all of these are going to lead to this state of increased ages, and they're going to age you, is not at all supported. And again, when it comes to fructose, we talked about fructose specifically in the last episode in terms of why we don't need to be concerned in particular about fructose causing glycation or fructation, but also just to touch really briefly on the impact of fructose on insulin sensitivity and blood sugar regulation. There's a good study here, which is titled Effect of Fructose on Glycemic Control in Diabetes, a Systematic Review and Meta-Analysis of Controlled Feeding Trials. So again, these are in patients with diabetes, where they're looking, and it's a meta-analysis. So they're looking at a number of different trials, looking at the isocaloric replacement of various carbohydrates with fructose. So basically, they would replace glucose with fructose in various forms in people with type 2 diabetes. And here's what they found. They state isocaloric exchange of fructose for carbohydrate reduced glycated blood proteins with significant intertrial heterogeneity. This reduction is equivalent to a 0.53% reduction in hemoglobin A1C. Fructose consumption did not significantly affect fasting glucose or insulin. So what they found here was that the replacing of other carbohydrates with fructose, which is supposed to be worse here in terms of insulin resistance, in terms of blood sugar regulation, all of that actually improved hemoglobin A1C levels, and this was in people with type 2 diabetes. So again, this idea that fructose itself is worse in terms of fructation and glycation we discussed in the last episode, the idea here that fructose is going to drive metabolic dysregulation, is going to drive insulin resistance, it's going to drive chronically high blood sugar is not at all the case. And I've also done a handful of episodes talking specifically about this with fructose and all of the misconceptions when it comes to fructose metabolism, why it doesn't just convert to fat in the liver, it doesn't just cause insulin resistance, and all the rest. So I'll link to those episodes in the show notes, but just wanted to touch on that briefly. But now moving on to the other side of the diet sphere, which is the low-carb ketogenic diets, and whether they're actually the solution to reducing glycation, as we're often told. This is typically the argument from that side, which is that you should be consuming a low-carb or ketogenic diet to reduce glycation. But what we actually find when we look at the literature, not only all the mechanisms that we talked about in the last episode, but when you look at the literature on glycation and low-carb diets, it's pretty interesting. And again, there's not a ton of literature on this because advanced glycation end products and dicarbonyls are not things that are often measured, that aren't often looked at in studies. There's not very many studies that are looking at different levels with different dietary iterations. But we do have some prominent ones, and one in particular is looking at ketogenic diets and the impact on methylglyoxal levels, which we know methylglyoxal is a major contributor to glycation, and it's 20,000 times more glycating than glucose. And so we'll take a look at a study here titled Ketosis Leads to Increased Methylglyoxal Production on the Atkins Diet. And they state, we found that by 14 to 28 days, methylglyoxal levels rose 1.67-fold, and acetol and acetone levels increased by 2.7 and 6.12-fold, respectively. So this is in a very short period of time where they were seeing a massive increase in methylglyoxal levels. They go on to state samples from subjects with ketosis showed even greater increases in methylglyoxal, 2.12-fold, as well as acetol and acetone, which increased 4.19 and 7.9-fold, respectively. While no changes were seen in samples from non-compliant, non-ketotic subjects, the increase in methylglyoxal implies that potential tissue and vascular damage can occur on the Atkins diet and should be considered when choosing a weight loss program. So pretty notable here. There's a number of things to touch on here. So one is, with just the general low-carb diet across the board, methylglyoxal levels rose considerably, but in the subjects with ketosis, there were even greater levels of methylglyoxal. So this trended with the level of ketosis. Basically, the greater ketosis you were in, the more methylglyoxal was seen. And this is also important because one of the common critiques of a lot of low-carb diet studies is that they're too short. And someone might say, oh, well, 2 to 4 weeks, that's not very long for a low-carb diet. But if you were to say, the general kind of expansion of that argument is you need more time to adjust and get deeper into ketosis and for your body to properly adapt to that ketosis. But if that were the case, then the people who were deeper in ketosis here, the people who were more ketotic, would actually have less methylglycol, and the people who were, low carb but not diving in quite as deep, weren't as adherent, actually would have had more methylglycol. But that's not what we find here. The people who were the most ketotic, they did it the best. They had the greatest methylglycol levels. And as they noted here, this is something that increases the potential for tissue damage, vascular damage. So definitely something to note here, and pretty remarkable when we're looking at the literature here on methylglycol levels on advanced glycation end products and showing that the low-carb ketogenic diets actually increase methylglycol. And we talked about this in the last episode, and they were kind of alluding to it in this, in the quotes we read in this study, which is that the ketones themselves, and specifically acetone, is a direct precursor to methylglycol, and especially when that acetone is used to produce glucose through gluconeogenesis, you see increased methylglycol production. It's one of the intermediates there. So, it's basically inherent to the nature of a low-carb ketogenic diet to see increased ketone production and, as a result, increased methylglycol production. And there are some studies actually looking at this more specifically, looking at the relationship between the ketone production itself and the methylglycol, or actually advanced glycation end products. We're going to look at a study here looking at this, and they're actually looking at rodent models who have type 1 diabetes, and they're in ketosis as a result of this, and they see what happens with, when they suppress that ketosis and the impact on advanced glycation end products. And so this is a study titled Citric Acid Inhibits Development of Cataracts, Proteinuria, and Ketosis in Streptozotocin type 1 diabetic rats. And they state, although oral administration of citric acid to diabetic rats did not affect blood glucose concentration, it delayed the development of cataracts, inhibited accumulation of advanced glycation end products such as CEL and CML in lens proteins, and protected against albuminuria and ketosis. So we're going to get into the mechanism of this in a second, but it's very important to note it didn't affect the blood glucose in this state of type 1 diabetes, and yet it lowered the advanced glycation end products, protected against the excess albumin as well, and reversed the ketotic state. And what they state is, later on, they state, we also show that incubation of protein with acetol, a metabolite formed from acetone by acetone monooxygenase, generates CEL, an advanced glycation end product, suggesting that inhibition of ketosis by citric acid may lead to the decrease in CEL in lens proteins. What they're basically finding is that by administering citric acid, which inhibits ketosis, decreases the production of these ketones, there was less advanced glycation end product formation. So they were able to isolate that mechanism in this, in this state, and identify that the production of the ketones is actually responsible for the methylglycol production and the age formation. So again, if we're concerned about advanced glycation end products, we might want to be a little bit more concerned about a ketogenic diet. It might be something to be aware of. Now, there is another factor to consider here, which is the impact of low-carb and ketogenic diets in general on oxidative stress, and as a result of that, on lipid peroxidation, which, as we talked about in the last episode, lipid peroxides increase dicarbonyls like methylglycol, and they increase advanced glycation end products. If we look at this study here titled Ketogenic Diet in Epileptic Children, Impact on Lipoproteins and Oxidative Stress, they state, our group has recently investigated lipid peroxidation in 26 children under the classic ketogenic diet and observed high levels of plasma T-bars. It's possible that ketogenic diets act as an antioxidant at the central nervous system, but induce oxidative stress in the peripheral system, thus contributing to a negative clinical prognosis. So those T-bars that they're referring to here, these are markers of lipid peroxidation and oxidative stress as well. And so what they basically found was that in these children on a ketogenic diet, they found increased levels of lipid peroxides, increased lipid peroxidation, which does not bode well when we're talking about glycation and advanced glycation end product formation. And it also doesn't bode well when it comes to the detoxification and clearance of the dicarbonyls and the ages. Now, the last point that's worth mentioning here, again, just because it seems to be an argument that will never go away as far as this argument that high-carb diets are going to cause glycation and, you need to avoid sugars, you need to avoid carbs. Due to that, it's also worth highlighting, should be obvious, but it's worth highlighting, that low-carb diets don't prevent glucose exposure. Even if you don't consume any glucose, your body is still going to be exposed to glucose. So if you're concerned about glucose and its glycation effects, this is not actually going to be a solution. And on one hand, we know this very clearly when we look at blood sugar levels and hemoglobin A1C levels in people on low-carb diets. And there's a couple things to mention here. So one is that if somebody is insulin sensitive and they're on a high-carb supportive diet, they should have healthy A1C and blood sugar levels that should be about equivalent of someone who's maybe in the early stages of a healthy low-carb diet, quote unquote, where we should see good low A1C and fasting blood sugar. However, what we find is in people who are on these low-carb diets over time, we tend to see that their A1C levels tend to increase sometimes pretty dramatically, along with their fasting blood sugar levels. And we've seen this in some pretty prominent carnivore advocates that have shared their values and have found, a lot of them, or a number of them, have had A1Cs that are in the pre-diabetic range. And then there's fewer, but Paul Saladino being a notable one, who had an A1C of, I believe, 5.7 in that pre-diabetic range, or at least in the border there, which then decreased pretty dramatically once they added carbs into the diet, shifted back down into low fives as far as A1C levels as they adopted more of the bioenergetic approach. And so what we're seeing there is basically this idea that you're going to have more glucose exposure when you're on a high-carb diet, not actually playing out, and that many of the people on low-carb and carnivore diets are seeing more glucose exposure in the blood as a result of their diet. Now, on top of that, we also know that there's still glucose in the tissues as well. We know that that's more important than the blood when it comes to glycation, but we know that there are still saturated glycogen stores on a low-carb diet after a little bit of time. Initially, there's not, they get depleted initially, but with time, the glycogen stores get refilled. And we also know that a lot of gluconeogenesis takes place to produce glucose, even in the absence of consuming any. And so there's still considerable exposure to glucose inside the tissues in this state of a ketogenic or low-carb diet. But there's something else that's notable. While there is exposure to glucose, there's also less metabolic flux of that glucose. There's less active metabolism of carbohydrates because fat oxidation and ketone oxidation is heavily, heavily favored, and these interfere with glucose oxidation. Talked about this extensively in the past, the Randall cycle episodes, and a handful of others that I'll link to in the show notes. But we know that fat metabolism interferes with glucose metabolism. But what that means is that in this state where you still have glucose available due to gluconeogenesis, and you're running mostly on fat oxidation and ketone metabolism, that you're going to be left with a lot of glucose sitting there and a lot of glycolytic intermediates that are available as well to glycate, which those are the main things that are a concern when it comes to glycation and dicarbonyls. And so this idea that, if we just avoid the carbs in our diet, we're avoiding the problem is not at all the case. It's actually something that contributes to the problem in many ways. And there's actually one other mechanism too that's really important when it comes to this low carb state and glycation. But the first thing I want to mention before that is that even on these low carb diets, there's still pretty notable glucose and insulin excursions, or spikes, if you want to call them that, in the blood, even without consuming any carbohydrates. And sometimes they're just as high as on a high carb diet, considering the insulinogenic effect of protein, and also how much you could see glucose increase even after low carb meals in people on low carb diets, on ketogenic diets. And they show that in this study. This is a study titled Glucose and Lipid Homeostasis and Inflammation in Humans Following an Isocaloric Ketogenic Diet. And they had people for 4 weeks on a normal diet, 50% carbs and 35% fat, and then 4 weeks on a ketogenic diet, which was 5% carbs and 80% fat. It was a metabolic ward study in men without diabetes. And they showed very clearly that they were effectively in ketosis. They had elevated ketone levels, elevated free fatty acids, and elevated glucagon. And what they found, and we'll see this in figure 1 here, is that the blood sugar increase, and they looked at the area under the curve, so not just the momentary spike, but the total amount of increase after the ketogenic meal for the people on a ketogenic diet was higher than the people who were on a high carbohydrate diet eating a high carb meal. It wasn't statistically significantly higher. It was basically not statistically significantly different. It was basically the same, but it was actually, if you look at the numbers, it was actually higher, which is pretty remarkable. But we can see that here when we're looking at the left, this is the carbohydrate containing meal. So when we look at the filled in boxes This is the people on the carbohydrate-containing diet eating a carbohydrate-containing meal. You can see a small increase in glucose, of course, but not too much. And then when we look on the right, the hollow circles, this is the people on a ketogenic diet eating a ketogenic meal. And their increase in blood sugar was about the same as the increase in blood sugar from the people on a baseline diet eating a carbohydrate-containing meal. So again, this idea that compared to a healthy carb-containing diet, you're going to have less glucose spikes, less increases in glucose in the blood is not at all what we're seeing here. And then the other piece that I wanted to mention is the gluconeogenesis piece. So we talked about this as one of the important reasons why you're not going to have an absence of glucose on a low-carb diet. You're still going to have glucose available for glycation if you're concerned about that. But it's also worth noting that the process of gluconeogenesis not only leads to glucose, but it also leads to the same glycolytic intermediates as glucose metabolism. So when we look at this figure here, if you're concerned about, which, you should be more concerned about these than glucose if you actually understand glycation, you would be concerned more about the triose phosphates, which we see in the middle there, the glyceraldehyde 3-phosphate and the dihydroxyacetone phosphate. These triose phosphates are precursors to dicarbonyls, and so they can be, they're precursors to these very highly glycating agents. But the thing is, we produce these in the process of converting glucose to energy and in the process of converting any substrate, whether it's glycerol backbones from fat or amino acids or acetone. Any substrate being used for gluconeogenesis produces these same triose phosphates, these same intermediates that are the major precursors for dicarbonyls and glycation. So this is just another reason why you're not going to be able to avoid these potential precursors, avoid these substrates when you're on a low-carb diet. And again, as we've talked about, a bit today as far as ketones go, and in the last episode, we can have glycation even in the complete absence of glucose, which you don't have on a low-carb diet. You don't have the absence of glucose. You still have considerable glucose available. But even if you had the complete absence of glucose, you could still have glycation from fatty acids, amino acids, and ketones. But again, all of the evidence here doesn't actually point to a low-carb diet being better for glycation. If anything, it points to it being worse. All right, so let's get into the kind of summarizing portions here. Let's talk about what actually is responsible for the accumulation of ages, which is something to be aware of. They do contribute to inflammation. They do damage protein. So if we're concerned about glycation or considering some concerns regarding glycation and advanced glycation end products, what is really responsible for, seeing increased levels? And then what do we do about it? How do we prevent that? How do we resolve that sort of state? So as we've kind of come to, throughout these two episodes, the main driver of age accumulation is impaired metabolism. And there's a number of things that go into impaired metabolism. But this is something, for example, that we see very clearly in type 2 diabetes, which is, a very clear example of this, a situation where there's very obviously impaired glucose metabolism and high oxidative stress and high inflammatory state. And we see in this situation a few different mechanisms that drive increased age formation and impaired clearance. And we've talked about these. We've talked about the increased substrate available because we're not actually using that substrate well. We've talked about the increased glycolytic intermediates that are available here. In the case of type 2 diabetes, we also have increased gluconeogenesis going on, which further adds to substrate there. We also see increased oxidative stress leading to more lipid peroxidation. We've also already discussed in the state of oxidative stress, we have impaired clearance of the ages and the precursors, the dicarbonyls. So there's a number of different reasons why we see this in type 2 diabetes. And we've gone through a handful of studies showing that, on kind of all sides as far as the state of insulin resistance and how that increases the accumulation of ages. But looking at a couple of other angles here, one of them is actually looking a little bit at some research on the relationship between glycation and the B vitamin, vitamin B1, or thiamine. And so this first study here is titled Increased Protein Damage in Renal Glomeruli, Retina, Nerve, Plasma, and Urine and Its Prevention by Thiamine and Benfotiamine Therapy in a Rat Model of Diabetes. And what they found were that there were 2 to 4-fold increases in fructosal lysine and H content of glomerular, retinal, sciatic nerve, and plasma protein in diabetes. And we know this. We know there's increased advanced glycation end products in diabetes. What they found was that increases in ages were reversed by thiamine and benfotiamine therapy. So this is pretty notable, and we're going to talk about some of the reasons for this in this next study. This is a study titled Toxicity of Glyoxalase role of oxidative stress, metabolic detoxification, and thiamine deficiency. And they state glyoxal cytotoxicity was prevented by increasing glyoxal metabolism with thiamine or NADPH generators and was increased in glutathione or thiamine deficient hepatocytes. So we're seeing that, again, both glutathione, which we already know, and also thiamine is important for clearing glyoxal. Going on to explain this a little bit further, they state thiamine in its diphosphate form, TDP, is an important coenzyme for transketolase pyruvate dehydrogenase, alpha-oxoglutarate dehydrogenase, and the branched chain alpha-oxoacid dehydrogenase complex, enzymes that are involved in the pentose phosphate pathway, which we touched on earlier, and citric acid cycle energy generation. This is mitochondrial energy production, which we've talked about quite a bit. Thiamine also increased erythrocyte transketolase activity and decreased methylglyoxal accumulation when erythrocytes were incubated with 50 millimolar glucose. So what we're basically seeing here is that thiamine is important for a couple of different aspects of physiology here when it comes to glycation. And this touches on two things. One is the importance of these different features of physiology and glycation, and then second, the importance of thiamine. So as they touched on here, the mitochondrial energy production is highly thiamine dependent. And so having enough thiamine is important for making sure that we're producing energy effectively, and especially so when it comes to glucose, which utilizes thiamine a bit more because of the pyruvate dehydrogenase enzyme. But then also, they mentioned that thiamine is important for the pentose phosphate pathway, a number of different enzymes that help in the regeneration of glutathione, which we talked about earlier in terms of glucose. So what we're seeing here, and kind of using thiamine as an example, is just the importance of the metabolic state when it comes to both the production of and the clearance of glycation and its products. But we're going to talk about another factor here, which is endotoxin or lipopolysaccharide. And this is one that we talk about all the time. Endotoxin is basically a component of bacterial cell walls, and it's produced by bacteria. So when we have bacterial overgrowth, when we have intestinal permeability, we see increased endotoxin absorption. And endotoxin is a primary driver of impaired mitochondrial function, impaired metabolism, and as a result, insulin resistance, fatty liver disease, neurodegenerative conditions, pretty much every chronic health condition you can think of. And of course, it also plays a role here when it comes to glycation. And they talk about that here in this study, which is titled, "Is methylglyoxal a potential biomarker for the Warburg effect induced by the lipopolysaccharide neuroinflammation model?" And they state, "We observed high serum and cerebral methylglyoxal levels in association with a reduction in glyoxalase 1 detoxification activity and a close correlation between serum and hippocampus methylglyoxal levels with the systemic and neuroinflammatory responses to lipopolysaccharide or endotoxin." So what they basically found was that there were a couple of things here. One is impaired detoxification of methylglyoxal. Then also that the systemic and neuroinflammatory response of endotoxin increased the production of methylglyoxal. And so when it comes to some of the main factors that we talk about that cause mitochondrial dysfunction, that impair our capacity for energy generation, which are at the crux of health, endotoxin is up there. That and PUFA, which we talked about PUFA a bit in the last episode, where it's susceptible to damage, lipid peroxidation, and that will increase advanced glycation end products. But endotoxin, of course, is right here with it in pretty much every chronic disease state and process you can think of as a major causative factor. And then one of the others that we did talk a little bit about today, and of course is always at play, is thyroid. And this study is titled "Increased Glycoxidation Products in Clinical and Subclinical Hypothyroidism." And they state increased levels of CML, which is an advanced glycation end product, were found in clinical and subclinical hypothyroid patients compared to controls. Methylglyoxal levels were also elevated in patients compared to controls. So what we're seeing here is the hypometabolic state, a low thyroid state, also being implicated in the accumulation of advanced glycation end products and dicarbonyls, which makes sense because of the implication, the number of different places where thyroid has an effect, on detoxification, on energy production, on glucose metabolism. And so, of course, when we really boil it down, if we're concerned about glycation, if we're concerned about ages and aging and the inflammation they cause, it always comes down to those same factors, which is an impaired metabolic state, impaired mitochondrial respiration, the resulting oxidative stress and damage that comes about there. And we just see it as an example here with some of these classic things that we know to cause mitochondrial dysfunction and cause oxidative stress, like endotoxin and polyunsaturated fats. And we also see it on the flip side with the things that support energy production that support mitochondrial metabolism, support detoxification, things like, the B vitamins like thiamine, as well as thyroid here. So with that in mind, let's talk a bit about the solutions. If we are actually concerned about glycation, what are some good steps that we can take, some of the primary steps that we can take to resolve that issue, to improve that state. And the first, of course, is doing everything that we can to improve the metabolism of the fuel coming in. And we want to remember that this isn't a fuel issue. It's not an issue caused by the carbohydrates, but rather it can be an issue of being able to utilize those carbohydrates or any fuel for that matter. And so we want to make sure that we're doing everything that we can to improve the metabolism of any substrate that's coming in. And this is what we talk about on the podcast in the last over 100 episodes, all of the different factors that can be implicated here. Endotoxin and PUFA being huge ones, but also nutrient deficiencies being big ones, sleep issues being big ones, hormonal imbalances being big ones, excess estrogen, lack of progesterone, lack of testosterone. When it comes to endotoxin, there's so much to dig into as far as, gut health and the different factors there and how to address it. But in a broad sense, all of these things that we, talk about pretty often, all of the foundations go a really long way when it comes to improving the metabolism of the fuel so that there's less available for glycation. And that kind of being the bottom line. Talking about a couple of other factors here, though. One is, of course, the fats that we're eating in our diet. So not only do the polyunsaturated fats, the omega-6s and the omega-3s, interfere with our ability to utilize the fuel, to utilize glucose, they themselves are also implicated in glycation because they're incredibly susceptible to damage, to lipid peroxidation, and this can then cause glycation. This can cause advanced glycation end product formation and ALEs as well, which we talked about in the last episode. So decreasing the polyunsaturated fats in your diet, favoring the monounsaturated and saturated fats in your diet goes a really long way. And, we've talked about this in many different instances. Obviously, reducing the seed oils is a starting place, but there's also polyunsaturated fats found in high-fat chicken and pork that are fed, corn and soy and high PUFA foods, fatty fish, nuts and seeds. These are all ones that we want to be concerned about when it comes to the polyunsaturated fats. If you're not sure about, which fish are high in PUFA or low in PUFA or which nuts and things like that, you can take a look at the Energy Balance Food Guide at jfeldmanwellness.com/guide. You can download that for free and take a look. I list out all the foods based on how well they support our metabolism, and the polyunsaturated fat content is a huge piece of that. So decreasing the polyunsaturated fats in our diet and favoring the mono and saturated fats is crucial when it comes to general metabolic health, but also glycation. And again, I list out the healthy forms of saturated and monounsaturated fats in the food guide. On to the next one being endotoxin. And not only does endotoxin impact the fuel utilization, but as we talked about, endotoxin is also something that will interfere with the clearance and detoxification of the glycation products. Now, this is a large topic. There's a lot that goes into lowering endotoxin, starting with eating easily digestible foods, lowering the hard to digest foods, things like grains, legumes, raw vegetables, and the grains and legumes that are not fermented, sprouted, well prepared. All of those tend to be hard to digest foods. They tend to be things that support the growth of harmful bacteria. They tend to encourage intestinal permeability. So those are all things we want to consider when it comes to reducing endotoxin exposure. There is a lot more that can go into it, everything from protein digestion to fat digestion. These are things that we've talked about in prior episodes. Intestinal motility being very important as well. Again, something that we've talked about in numerous different episodes, the different factors that can impact that. But we definitely want to make sure that we are addressing that whole area. And then there are some things that we don't talk about quite as often that are a little bit more specific to glycation. And one of those being supporting the glyoxalase system, which, as we talked about, is largely dependent on glutathione. And there are a handful of things that are important for increasing glutathione. We talked about glucose and insulin, consuming carbohydrates, basically being really important for supporting glutathione and glyoxalase. We also have the amino acids that make up glutathione, which is 3 amino acids, glycine, cysteine, and glutamine. And so getting enough of each of these is also really important for producing glutathione. I would say for most people, if they're eating enough protein, the cysteine and glutamine kind of take care of themselves. When it comes to glycine, this is one that's harder to get if we're not getting the connective tissue-based proteins, either collagen and gelatin as supplements or in bone broth or in collagenous meats. Those are really our main sources of glycine. So, and glycine is really important here when it comes to producing glutathione. It's also important for tons of other things, including gut health, as we were touching on. So those three amino acids are all important for producing glutathione and supporting the glyoxalase system. We also have a number of vitamins and minerals that are generally supportive of this system because they are important for antioxidant production, some of them glutathione and some other antioxidants. And then also they're important as antioxidants themselves for helping to prevent oxidative stress. So that would be vitamin E and vitamin C being antioxidants themselves that can help to lower oxidative stress and spare glutathione. And then we also have minerals like selenium, zinc, iron, and manganese, all of which are important for antioxidant production. Now, I should say this doesn't mean that we need to take a supplement with all of these minerals or vitamins. These are really things that we should be getting enough of in our diet if we have, a good bioenergetic diet. But we would want to make sure that our status of these is pretty good for tons of different reasons. I mean, these vitamins and minerals play so many different roles in our health, but just in the terms of this conversation, they're all important here when it comes to the glyoxalase pathway and general detoxification and supporting the reduction of oxidative stress. So that again would be vitamin E, vitamin C, selenium, zinc, iron, and manganese, as well as those three amino acids, glycine, cysteine, and glutamine. And then the last area that's important to touch on here is making sure that we're not driving excessive oxidative stress, considering that doing that does deplete glutathione. It does interfere with energy production. It does actually lead to further damage, and it's not actually the solution for improving the clearance of ages of glycation products or improving their detoxification. So this would be basically any of the kind of hormetic interventions. And of course, with the knowledge in mind that yes, these stimulate the antioxidant systems, but by definition, they do so by increasing oxidative stress and damage, which is not actually a solution for supporting the system. And so this would be things like calorie restriction, carbohydrate restriction, low-carb diets, fasting, resveratrol, cold exposure, cold plunges. There are a number of other supplements, interventions that are recommended when it comes to hormesis. And in general, we'd want to be careful around any of them because they are going to be driving oxidative stress in the process of their supposed benefits, which in many cases are not actually benefits. They're just features of the research that's kind of poorly constructed. Again, we've talked about this in detail in those hormesis episodes. Along with this, it's worth mentioning that excess exercise, which exercise is beneficial despite the stress that it causes, but excessive amounts can certainly lead to increased oxidative stress and the damage that results. And then when we're talking about excess oxidative stress, it's worth mentioning, especially because I mentioned this when it came to glutathione and the antioxidant systems, which is iron. So having enough iron is incredibly important. It's a very important nutrient. We need it for energy production. We need it for the antioxidant systems, but also excessive amounts of iron can be a driver of oxidative stress and often an underappreciated one, especially in the conventional medical space. So we do want to be careful of excess iron as well. We want to make sure that we're monitoring our iron status with, occasional blood work and that we're aware of our iron balance when it comes to our diet as well. So in general, those would be the main things we would want to focus on when it comes to glycation. Notice that at no point did I mention that we need to avoid carbohydrates or avoid sugar, as those aren't drivers of the impaired metabolic state. They're drivers of oxidative stress here. And the real things that we do want to be aware of when it comes to excessive glycation really come down to those things. And again, in many cases, or like many cases, it comes back down to the fundamentals. All right, so we will wrap up this series there. If you did enjoy it, please leave a like or comment wherever you're watching. And also please leave a review or 5-star rating if you're listening on iTunes or Spotify or somewhere else. All of those things really do a lot to help support the podcast and are very much appreciated. As always, to check out the show notes where I'll link to the studies and articles and anything else that I referenced throughout today's episode, you can head over to jfeldmanwellness.com/podcast. And if you're looking to optimally support your metabolism, lose weight, improve your digestion, get amazing sleep, rebalance your hormones, boost your energy, and so much more with clear action steps and strategies alongside personalized guidance from me, then head over to jfeldmanwellness.com/solution, where you can find all of the information for the Energy Balance Solution program. This program includes customized health coaching. It includes a video library with videos on how to best regulate blood sugar, how to restore gut health, how to lose weight without destroying your metabolism, how to boost your metabolism, how to get amazing restorative sleep, how to rebalance your hormones, and tons more. It also includes resources like sample meal plans, recipes, the calorie and macronutrient calculator, as well as a supplement guide and a private community. So head over to jfeldmanwellness.com/solution to check out all the details. And with that, I'll see you on the next episode.